Okay, so welcome back to the second part of our lecture 7. And in this part, we're going to learn about Scikit-Learn. Up until now, we have been programming all of our algorithms from scratch. I think that it's important to start the semester that way in order to build confidence with Python programming and observing at the same time how you can implement the theory in code in a professional way, right? And that's good. That's really nice, especially like if you're possibly doing like a research problem and designing your own algorithm, you need that experience, right? And that's like, again, that's why we did it. However, in practice, that's not what you're going to do. If you're working on like with a team of developers on an app or a project in industry, you're more than likely, if you're doing any type of machine learning, you're going to use Scikit-Learn. Scikit-Learn is the go-to standard machine learning library in Python. And you can do a lot with it. You can look at classification algorithms, regression algorithms, you can do clustering, so that's like unsupervised learning. You can do pre-processing, dimensionality reduction, and all kinds of things. And it's built in for you. You won't have to write the algorithms yourself, right? And I know that last time I mentioned TensorFlow and this other thing called PyTorch. Those libraries are deep learning libraries, right? And yes, Scikit-Learn has a deep learning class. However, if you're going to use deep learning, you should probably use TensorFlow or PyTorch. But at the same time, not but like when you're dealing with the problem though, you don't want to jump to neural networks. You want to try the simplest algorithms first. So in practice, all of the problems I've ever dealt with, I've never needed to use TensorFlow. Well, one problem, and it was like a financial type of problem. I used deep learning, but other than that, logistic regression, k-nearest neighbors, these simple algorithms will probably be better. But then again, things are changing. Data is becoming more complex. The target functions that we're trying to find are getting harder and harder to find, right? With the data that we're observing. So, but again, Scikit-Learn is awesome, right? And it's what you'll use in practice. And that's what this part of our lecture is about. Just learning how to use it, what like its functionality is, what the methods are to a classification or regression algorithm are, and just understanding what it is and seeing how easy it is to implement. Now, I originally planned for us to walk through several different learning algorithms that we know of, but I don't know if we'll have time. So we'll at least look at k-nearest neighbors using Scikit-Learn. And if time permits, we'll do logistic regression and a deep neural network and whatever. We'll like pick one at random and see what it does, right? So we're going to perform k-nearest neighbors on the iris data set as before, but this time we're going to look at binary classification. Okay, instead of having the 3 different flowers, we're just going to look at 2 of them. So that's what's going on right here. Right, so this is, I load in my data with the iris data set. So actually, I should go back up. Import the 4 standard libraries, set my theme. I'm importing a k-nearest neighbors classifier from Scikit-Learn. And I'm importing train test split. I load my data using Seaborn, so the iris data set. I make a data frame of all rows that do not have a entry setosa in the species column, right? So that'll be the Versailles color and Virginica flowers rows. I create a feature matrix of sepal length and sepal width. And then it's typically going to be best practice to convert your labels to a numeric type. So that's what this function here does. It just says that if y is Versailles color, return 0, else return 1. And I chose 0 and 1 because if we want to use logistic regression, that should be the best labels to choose. like later if we have time. And then here, I don't know if you've seen me code this before, but I wanted to take the current iris species column and I wanted to apply the make labels function to that. So the way that we can do this is with the .map method. So iris species .map and then throw in your function. And it's going to broadcast onto that. So each entry of that pandas series will be passed into this function. And then I convert it to a NumPy array. It's a really convenient tool, especially like, because a lot of times you'll have data and you want to change it, right? In a data frame, and you can do that. I make my train test split as in the lecture 7.1. And then here I instantiate k neighbors classifier and I pass in the keyword in neighbors equals to 7. And I give this the name CLF. CLF is an abbreviation for classifier. You'll see that often when you're reading tutorials and docs and things like that, that you'll define your classifier as CLF. Or if you're doing regression, it'll be reg-R, so like REGR. So I hope that I've emphasized it enough throughout this semester that everything in Python is an object. And objects have attributes and methods. So this is an object. What are its attributes and what are its methods? What are its parameters? What do you pass it? So as you probably know, or as I've mentioned before, Python is probably one of the most well-documented programming languages that has ever existed. And Scikit-Learn is a prime example of that. The documentation is amazing. So here is the documentation for the k-neighbors classifier. It's inside of the neighbors module, which is a module inside the Scikit-Learn package. Okay. So these are the parameters that you can choose to instantiate it with. Notice that they're all keywords. So you don't have to pass it any parameters. By default, the number of neighbors, or k, is 5. Okay. And then there's weights. There's different ways to perform the algorithm that we haven't discussed, so we can just ignore that. But I encourage you to read about it and play around with them. It's going to be really easy to do that once you understand the API. Okay, here are the attributes. We have classes, metrics, features, all sorts of things. And this is what I'm telling you right now with k-neighbors is going to be similar to other classifiers and other regressors inside of Scikit-Learn. So next up, we'll have like an example of it, but then we have our methods. Methods are going to be very important. So pretty much every classifier and every regressor in Scikit-Learn will have a fit method. Okay. And then also a predict method, a score method. And then the other ones are kind of are specific to the type of algorithm. But I'll just go ahead and say it. Every classifier, every regressor will have fit, predict, and score. And then the other methods vary depending on the algorithm. Okay. Also, I think a lot of them will have predict probability of being a label as well, if it's a classifier. Okay. So I encourage you to read the documentation after today's lecture. Okay. So this is me instantiating with the keyword in neighbors equal to 7. Okay. Now, if you remember with our single neuron model and our deep neural net, we had a train method, right? Like we wrote our own classes and then we do .train and we pass in our training data. The analogous method for Scikit-Learn is the fit method. So what we're going to do is we're going to pass into fit, xtrain, and ytrain. Now, just as in our custom classes that we wrote for the single neuron and the neural network, if you have a feature vector, right, and your features only consist of one feature, you have to do .reshape -1, 1, right? I kind of built those classes so that you would have a feel for how to use Scikit-Learn now that we're here, right? So all of the same things that we had to do, you have to do here as well. And this will be a NumPy array. And again, this will be a NumPy array as well. You can, we could have fit with string labels, But again, it's best practice when using Scikit-Learn to go ahead and convert them to numeric labels. Okay. And this fit method, it's been trained. Okay. So once it's trained, you don't have to train it again. Right? It's done, just like with our custom classes that we wrote. So next up, we're going to make a prediction, right? So we call the predict method and pass in our testing data. Okay, so this will print it out. I don't know why I did it in this order, but whatever. And then I assign a variable, yPredict, equal to the prediction, right? So it's making a prediction on each entry in X-test, right? So it's returning a vector. Okay, and then I can like double equals, does that equal to Y-test? This will be a Boolean array. And then I can sum that Boolean array, it's either ones or zeros, right? And then divide by the length to get my accuracy. So there you go. So he's just printing out so you can see exactly what's going on. Okay. Now, instead of doing this though, we could call the score method and pass in X-test and Y-test. Here's our score, and you see that they match up. Okay. And again, if you forgot what score did, you would go to the documentation, score, return the mean accuracy on the given test set. Okay. So next up, we're going to visualize the decision boundaries, right? This is a classifier, so there should be boundaries. And we're going to use that nice plot decision regions function from mlx10.plotting. All right, so we set our fig size, call our function, label, and then just show the thing. It takes a second because it's making a mesh grid behind the scenes and then predicting on that mesh grid the labels. This looks different than the decision boundaries that we saw before, right? The other ones were lines, hyperplanes. This is definitely not a hyperplane. Now, a neural network would have a curvy decision boundary as well, but we didn't really look at that then. But the perceptron and linear logistic regression, they were linear separators, right? This is not. So it's another toolkit, right? You can possibly imagine where this would be a much better classifier than logistic regression, right? Like if there was like, I don't know, data like in a circle right here, there's all red points and then blue points inside, then k-nearest neighbors would like be perfect, right? So it's important to remember what these things are actually doing when choosing between them, right? So I think this plot's actually pretty interesting in how it's like growing down here, and you can see that there's like these red plots kind of taking up all that area there. Okay, so notice that we've done everything that we did in lecture 7.1, right? We literally just like called the fit and looked at the score. We did more than we did in lecture 7.1, right? So this is actually kind of dangerous though. Not dangerous, but it can be bad. Because a lot of people will learn to use an API like Scikit-Learn, and they'll treat it as like a black box solution to a problem without understanding the actual algorithm that's hidden underneath. So it's always a good exercise to try to program the algorithm on your own before using a black box like this, so that you understand the pitfalls and the dangers between choosing one over the other, depending on the data that you're looking at. Okay. So just keep that in mind. All right. So up until now, we haven't been looking at anything as far as like model performance, really. We've looked at like classification error, we've looked at accuracy, but we haven't really examined the performance of our algorithms. That's bad. Right? In practice, you really want to look at how your algorithm is performing on the testing data. So The simplest way to do that is with something called a confusion matrix. Okay. And a confusion matrix is a table that is used to describe the performance of a classification model. Okay. And well, I think I just highlighted here. The confusion matrix shows the ways in which your classification model is confused when it's making its predictions. So it's going to show us where, or not where, but how many times we predicted the wrong answer and how we predicted the wrong answer. And I chose binary classification to kind of illustrate this point. All right, so that's what we're gonna look at next, and then we'll talk about the visualization that we see. So I import from metrics the confusion matrix. I instantiate another model just because I wanted to. I fit it again, I predict again, and then I calculate the confusion matrix here. You pass in y test and y predict. Okay, I print that out. And then I'm going to visualize the confusion matrix using Seaborn. So I set my fig size, and then x is equal to SNS, so that's the Seaborn alias, dot heat map. So I'm going to use a heat map here. Pass in the confusion matrix, annotate it to be true, set a C map equal to blue, and then no color bar. So typically when you plot a heat map, there's a color bar indicating intensity on the right, and I don't really want to look at that. Set my title, X label, Y label, and then my tick labels, and you'll see why they're this in a moment. All right, so up here, that's the confusion matrix. And then down here, we have this, okay? Now, in binary classification, we can think of, well, actually, I have a little thing down here. We can think of the assigning of labels as like positive and negative, like heads or tails, right? Or 1 or 0, right? So we can think of label 1 as like a positive event, okay? And then label 0 as a negative event. Using this terminology, we'll say that a true positive is so for correctly predicted event value. So if you predict the label 1 and it is a 1, right? False positive for incorrectly predicted event value. So if you predicted a 0, but it should have been a 1, right? And actually, I think that I wrote this well enough to where you can read it. I would like to just talk about like looking at this thing, right? So you can think of this as like 0, 1. These are our predicted values here, right? So we predicted 13 of those points to be true. So label 1, right? And then this row corresponds to all of the label 1s, or yeah, right? And then this row here corresponds to all the label 0s. So we predicted 3, so there's 3 predictions to be true here, but they were false or label 0. So on the diagonal, you have like your correct values, right? And then here we have these other values like false positive, false negatives that you'll see down here. So it's just a quick and easy way to visualize what your model is doing, right? Now, why not just consider like accuracy, right? Well, sometimes these like false positives are more important to what you're doing than just how accurate you are, right? So like imagine like you're like doing like drug testing, like clinical trials or something, right? And like if you have like 3 people that die from your medication, that's more important than like this other collection that where the prediction, like it worked, right? It's like good or bad. That's like a simplified version of the idea, but I hope it's clear, right? Or like with self-driving cars, you don't want like any like things to veer off the road, right? So just like understanding the problem that you're dealing with is important. And this is the easiest and quickest way to kind of visualize that. And I'll provide more links to these topics later today, right? because of the nature of this course and how much we have to cover, because it's like learning to program in Python, data science, and machine learning and the theory, I can't squeeze it all in. So I'll provide links, and they'll be actually with the YouTube video as well, like just links to click on. Okay. So going down further, all right. So precision. So now we're going to talk about some other metrics for measuring performance. So this is a visualization, but we want some numeric values to kind of interpret these things. So precision is defined as the number of true positives divided by the number of true positives plus, oh, look at those typos right there. Have to fix that. Where is it? Plus the number of false positives. Okay. False positives, right? So, okay. And then recall is defined as the number of true positives divided by the sum of true positives and false negatives. So can someone tell me, like, just looking at that matrix, like, okay, again, true positive, correctly predicted event, incorrectly predicted event for false positive, true negative for correctly predicted event, or for correctly predicted no events, that's like the 0, right? So no events 0, event 1. Okay, clear? So looking over here, I don't like how y'all are looking right now. Maybe I should pause on this and go over it again one more time. So if I'm looking at this matrix, can anyone tell me where the false positive would be? Like, right. That's the false positive entry there. In this entry here, true positive, yeah, right, okay. So good. And then this entry here, right, false negative. And then, right, yeah, okay, y'all all got it. Okay, just took a second. So okay, again, the 3 is what? False positive, and this is true positive, right? So true positive, false positive. So the precision is going to be 13 over 16, right? And then the recall is going to be over 19, right? So you see how it's related to the matrix, those values? So it's like the number of correct values divided by that sum is your precision. Number of correct values divided by this sum, recall. Okay. And then there's also this concept of the F1 score, which is the harmonic mean of these values. And these numeric values tell you about the data. Not the data, I'm sorry, about how your model is performing. There are different ways of measuring performance. Okay. And I wrote like a little paragraph here. I don't know if I want to read all this out. Actually, I should probably say something about this. So I think I got this actually from Scikit-Learn maybe. So note that the precision may not decrease with recall. Okay. So precision and recall, these things, how do they relate? And that's what all of this is saying down here. So the definition of precision shows that lowering the threshold. What is the threshold? So in this case, we don't really have one with k-nearest neighbors. So I hope we can make it to logistic regression so that this will make more sense. So on that note, let me go down and see if I can get there, and then we'll come back up to that. Let's just look at this report here. Okay, so from Scikit-Learn metrics, we're going to import the classification report. Okay, so print this out, pass in y-test and y-predict. We get this table. We see our accuracy right here, right? We see our accuracy there. And then here are precision, recall, and F1 score. okay? And again, sum over the column, sum over the row, right? And you can do that for each one, right? That might not have been clear above either. Like, so like the precision for 0, right? We what? The number of correct entries over that sum, the row sum, right? So for each of those values, so for each of the labels, you're going to have these numeric values, precision and recall and F1 score. Ignore the support column for now. So maybe this can help us understand something. So look at the recall for label 0 and look at the recall for label 1, okay? Recall is the sum, is the true positives over the row sum, right? So this value is slightly larger than this value. So let's come back up here and say, so 0 recall is slightly larger than 1 recall. So here's like 0 recall would be what? So it's across the row. Wait a minute. No. Yeah, it is a row. Sorry, got confused for a second. So it's 11 over 14, yes. So, and then here it's 13 over, these values are too close to each other to really, let me choose a different K real fast and see if I can make this, let's say like 3. Whoa. So I immediately see that we're doing like, so let's go back down here to our report. Yeah, recall 71 versus 41 here. Or 0.71 versus 0.47. Sorry. I'm scrolling up and down too much and it's confusing. Right? So you can see that. You can see which this is telling you immediately this difference here. So like on this row here, there's 10 versus like the 4 in a sense, right? But on this row, it's like 9 versus the 10, right? So we were doing well with predicting the zeros, the 0 class, right? But it basically 50% on predicting the 1 class. Does that make sense? I think making the numbers jump different kind of illustrated it better, right? So that is so the recall, that's a good example for the recall. The precision is about the same for whatever reason here. No, it's not. It's not the same. Yeah, it's so 50 versus 70, right? So the precision for 0, so that's like the column, right? So, oh, yeah, you can see that, right? The precision was higher because look at the 9 and the 4 and the 10 and the 10 there, right? And that's along the columns. But the recall along the rows, 0 is better, right? But notice that like precision is better for 1 versus 0, recall is better for 0 versus 1. Look at the F1 score, they're basically the same. Harmonic mean, right? The average, right? Between these two, right? So if like between the two of them, it's terrible, this is going to reflect that. Or like if they're like, yeah, so like if 1 is good here and 1 is good here, then that's reflected here, right? So now that we kind of have a better sense of these values, we can look back at the F1 score with the 7 neighbors that we chose. Actually, I think, let's see, like 17. 7 might have been better. Yeah, 7 looks better than that. The heat map actually gives me an immediate visual stimulus about what's going on, right? If the dark squares are along the diagonal, I know like we're doing all right. Another like visual cue, like that's why I use these things because they're quick. as you can probably tell, like I'm getting confused myself, like going back and forth, because I typically just look at the heat map, right? Like in my own stuff, that's what I look at. So F1 scores are still, they haven't really changed much. Wow, our accuracy is terrible now. Did we choose 7 or 5 earlier? I thought the accuracy was better earlier. Oh, there. F1 score is higher now. You see that? Good catch. Yeah, I didn't run that cell. So yeah, the F1 score is higher because the precision and recall, like they're better together, right? For both of them, right? So interesting. Now, there should be a very glaring question. Like it's just, there's something that y'all are good at asking questions. I'm surprised that no one has asked about yet. And I mentioned it in lecture 7.1, right, the first half of this lecture. When we split the data into training and testing, there's all kinds of ways to do that, right? How do we know that the training data that we have isn't skewed in some way, right? Like you randomly are shuffling this data and you're picking out a training set. How do you know like that one is like, how do you know it's not skewed, right? Why not pick another collection of features, another collection of data to train on that will better your model, right? So for example, like up here, let's change this random state to like 39 or something. Just pick another random state. This will generate a new training set and a new testing set. So run that. Oh, look at that. It went from 77 to 63% on the accuracy or the score. What does the decision boundary look like now? Looks different, right? So this should be like a red flag, right? The choice of your training data is important to the performance of your model, right? Especially like thinking back to the parametric models where that data that you use to train on is used to update the weights and biases throughout training. So if you selected like a bad training batch, like what's going to happen, right? So let's go back down here to our confusion matrix. Look at that, with this new set of training data. So this is a problem. There is a fix, but this is a problem that we should be concerned about. And depending on the rest of today's lecture, we might talk about it for a moment, but more than likely, we need to dedicate like a good 30 minutes or so to the fix for that problem. Yeah.
Just kind of going back to the table that we have at the bottom of the code, there's why we have custom precision recall and F1 scores for each of the variables. I don't know why that depends on.
So it depends on, this is, I said this, but I don't know if I emphasize it enough. You can set your event to be whichever label you want, right? So if your event is 0 and your non-event is 1, you get a precision, right? If your event is 1 and your non-event is 0, you get this precision, right? So you just do it for each one. And yeah, I probably wasn't clear with that earlier. Other question.
You were talking about how to choose the samples. It's like sampling, right? You could do it like randomly. So you can use another technique like stratification, for example, where you like identify some like features of the data and then try to get the sample, try to have the same proportion, and then you make
Right. There's where, yeah, you want to have like you want the distribution of your measurements to be like kind of nice, right? but even then, like there is a way that you can deal with these types of problems, and it's called k-fold or fold. Let me look it up real fast. I don't want to. It's just cross validation. I don't think like I don't want to go into it today because I want to spend like a good 30 minutes on it. But so basically, what you can do is just partition your data into like 10 subsets, right? 10 disjoint subsets, and then use 9 of them to train on, and then test on the one you left out, and then add that one to your training data, take one out, train on that data, and then test there, and then go through all of those, and you can evaluate how your model is performing on average with these types of things, right? And you can like pick the best out of all of them, and then you can use that for the true data that you left out, and then test on that. So it's almost like creating an artificial, it's like creating like 3 types of sets. You have train, validate, and then your leave out set, which is your like your testing data. Right? That's how people do it in practice. Question? No, it doesn't necessarily. So the different performance on the different data sets that you have, it doesn't necessarily mean that you're overfitting. It just means that the data that you're training on is not representative of it's like skewed in one way or another. Like you can have problems with for example, if you like with the iris data set, right? Like, where is it? Like if our training set consisted of like all those reds and like maybe 3 magentas and 3 greens, if that was your training set, that's not representative of anything. And that would dramatically affect your performance on the testing data, right? So it really is about just like cleverly partitioning your data in this like k-fold cross-validation method that we'll implement next time. But what I'd like to do now, though, instead of doing this cross-validation, is see if we can find another model that performs better on this data set that we have here. Which right now, the performance of k-nearest neighbors is not like it's 73, but like, I don't know, can we do better, right? So what I'm going to do is, and I specifically left this out of the notebook, because I want to like show you how you can just like go onto Scikit-Learn and find what you want to do. So you want to classify something, it's binary classification. So maybe go to like the user guide up here. And then do we recognize any of these names? So like maybe linear models. Maybe we can just search like up here, logistic regression. Oh, it's inside of linear model, as we should have guessed, right? Because it is a linear model. Here is logistic regression. Attributes and methods. It's inside linear model, that's where we get it. So I'm just gonna copy this here, come back over to VS Code, and then I'm gonna say that, and then I'll say CLF2 is equal to logistic regression, like that. And let me look at the parameters of this model. What do I need to pass it? It should be the case that we don't really have to pass it anything. Max iteration is 100. Maybe I'll change that parameter there. So it's max iter. Max iter. Maybe I'll set that to be like 1,000, like that. Okay. How do I train it? Dot fit, right? Throw in our X train and our Y train, like that. And then we can say logistic Y predict equals CLF2 dot predict method. Pass in our X test. I'm just gonna maybe again, I just made a new classifier called it CLF2. It's the logistic regression classifier. I fit it, and then I make a prediction. And then what I'm gonna do is come back up here and just copy this cell here, like right there. Just copy all that, come back down here, paste it. Actually, no, I wanna first, let me make a new code cell below this. I'll do that after. Again, I copied the other stuff. I just have to change this to be log y predict now. And then I want my this thing. I want to look at the boundary that it finds. I know that I'm moving fast, but again, I'm just copying and pasting everything. So X, Y, and now the classifier will be CLF2. That's the one that's going to be equal to. There it goes. As we should expect, it's a hyperplane. It's trying to separate that data. I don't know what its performance is. It's hard to tell from this, but that's why we have this confusion matrix, right? So again, the only thing that I typed different was that in this right here. And I just copy pasted everything. Okay. So let's look at the matrix. So log y predict. Everything else should be the same. Oh. We make sure that it actually is, yeah, it is calculating a new confusion matrix. It looks the same though. That's surprising. I did not expect that. Let's look at the classification report. (64% accuracy, precision and recall. So our recall for label 1 is actually pretty good. So if we were concerned about the recall there, which is along the row, yeah, I always forget. So yeah, and it's true, like 14 and then the 5 right there, we see that that's not bad. Question. Oh, thank you for that. Yeah, the recall was still high. Accuracy was 64 now. I don't know what it was before, but we haven't improved anything. It seems that our train test split was especially detrimental to our training here, right? I wonder what happens. Let's just let this go like 10,000 times. Does it do any better? Nope. All right, we need to try something else. And I'm not even sure that we'll be able to do better right now. I don't know if we have the tools yet. We don't know how to cross-validate. We don't know how to, there's algorithms that we don't know, right? Like, but let's just see if we can pick one that we do know. Let's try a neural network. We want a classifier, so NLP classifier. I'm just gonna copy all that, come back over here, the VS Code, paste that in, get rid of that, get rid of that, get rid of that. I'll call this CLF3. That's your learning rates. Those are your hidden layer sizes. I'm gonna change that to 60 by 60. Random state 1, that's how you initialize your weights. This is just a solver. You don't have to provide it one. It's a keyword, it looks like. So that learning rate is also very small. I'm gonna change that and like that, maybe. Who knows? And then I bet you, so if I click on the documentation, there seems like there might be a max iter. It's set to 200. That's probably too small for me. So I'm going to change max iter. Let's just say 10,000 times maybe. I don't know. So CLF3.fit, pass in X train, Y train. And then I can just copy paste everything from up here. So let's look at this. Copy that, come down. I'll say net y predict CLF3, CLF3, CLF3. So let's look at the decision boundary. It's curvy, right? And that's because it's a nonlinear solver, right? I don't know. See, sometimes you can kind of guess the precision and recall, like roughly, just by looking at percentages of the points that are in the wrong space, right? Yeah. So what was your guess just now? So 70 for precision or recall? Precision, right? Let's find out. So let's look at its matrix, calculate that, go grab that, and now it's net y predict. Something is weird about that. Y test, net y predict. It might actually be the case though. I wonder. No, I'm definitely plotting. I'm assigning the variable here to the confusion matrix 7, 7, 8, 11. Net y predict is right here. CLF3, predict on X test. So it really is giving me the same thing, which means that if I look at the classification report, it's going to be like the same. So oh, look at the accuracy though, right? That's terrible. And you can kind of tell by like, look at all those blues and look at all those oranges right there, right? So I'm actually glad I did this because the simple linear models that we were doing, and even k-nearest neighbors, is doing better than this deep neural net with 60 nodes in each hidden layer, with 2 hidden layers, right? Now, and like both of these, yeah, it's just the accuracy is awful here, right? So let's like go all the way up to the top now, and I'm going to pick like a different one. So like maybe like 13 or something, right? So a different train test split. Run that cell, just going to run all of them below. So this is k-nearest neighbors again, the first one. Definitely different regions of space. It's hard to tell if it's doing better, but we'll see. That's why we have all this other stuff. So across this row, right? So the recall is looking pretty good for label 0. Not so much for label 1, right? However, precision looks, no, precision's not bad, not good either, right? This on this column here. Well, it depends on what you want, right? Like if you're just concerned about accuracy, then you might not even care about precision or recall. But if you're concerned about these false positives, or like, then you need to look at it. Right? If you're concerned about if you're concerned about where you're predicting the wrong value, right? Question? So would a very high precision indicate overfitting for a specific type of like label, right? Yes, that could indicate that, right? But I think more so in this case, in this instance that we're running right now, it's probably indicating the training data what it's doing, like what the training data is doing, right? So I encourage you to actually go back and plot the training data and see what, like, where it is, right? Is it skewed one way? Or are they all like kind of in one side of the plane, right? And it's like, it's kind of interesting to do that. Right? So accuracy is 70% right now for k nearest neighbors. Going back to this, let's do logistic regression. There's our log separator. Oh, look at that. So if you're concerned about precision and recall now, this is looking pretty good. This is the best we've seen so far. And then let's look at our accuracy is 85%, right? F1 score is high too. Up here, the F1 score was not great for label 1 in particular, the harmonic mean of these values. But this is looking good. This is the best model so by a lot now, right? 93% here for precision, right? So that's the column for label 0. Yeah, they only missed that one value there. That's like, it's almost white, right? So let's try deep net now with, okay, there's our decision boundary. It's basically the same, right? Maybe if I change the learning rate. Forgot to do that last time. Let's just make my computer run for a while. So maybe like, still having a hard time, right? But if I increase the depth, I mean the number of nodes in the hidden layers, still not doing very well, right? But not any better than logistic regression. Okay. Yeah, it's basically the same as logistic regression. So it's not like, and the perceptron is not going to do any better than logistic regression, right? So out of all of the models that we have here, like out of the 4 algorithms really that we know about, logistic regression seems to be the best, right? And yeah, I'm pretty sure that you could, like we could, I don't know. I can't see a neural network doing better than logistic regression right now, but yeah, a neural network could do better, but it really doesn't, like, it depends on the training data, right? That's the most important fact here, right? Which means that this is a good illustration of what you should be worried about in general when you're working with like real world problems. You have a limited amount of data. You might have a lot of it, but it's still a finite amount, right? And that data is going to determine how your model learns. And the outside data that you don't know, like it's something to be very wary of, right? So I think this will finish lecture 7.2. So I'm gonna go ahead and stop the video here.